Alright YouTube, so let's do another problem. This time we're gonna do putnam A5 2018. So let f be a function, real continuous function, infinitely differentiable, such that f0 equals 0, f1 equals 1, and fx is greater than 0 for all x in R. We want to show there exists an n being a natural number, x a real number, such that the nth derivative of f is less than 0. The way to approach this problem is by way of contradiction. So suppose for all x in R, for all n the natural number, the nth derivative of f is always greater than or equal to 0. Okay, now let's expand fx by Taylor expansion. So that becomes this expression. Well, this is just the formula for Taylor expansion. Now let's choose x not to be 1, and let's let x equal to 2. So this becomes x2 2 minus 1, that's just 1. Okay. So so we know by our assumption, all those terms, this is always greater than or equal to 0 for all k, right? So that means this is always positive. So that means f2 is always going to be greater or equal to the finite sum So that also means, well, we can conclude this must be 0. The last term must vanish. Okay, now so this is our first claim, and our second claim now is this is always true. For all k and all x in the between 0 and 1, this is always true. Well, this is our first claim. So let me just claim 1. This is our claim 2. Well, why is this true? So let's prove this by induction. If k equals to 0, then kx is less than f1 for all x in between 0 and 1. Why is this true? Oops, did I click on something? Is it hello? Oh, okay, there we go. Okay. Alright, so why is this true? Well, it's true because okay, so this is always positive. So in some interval a and b, we can always find c such this is true, right? Now fc is always greater than or equal to 0, and let a equal to 0, let b equal to 1, we get 1 minus f0 equals to fc. Okay, so this means 1, so this means we have no, I'm sorry, let a equal to 0. B, we don't fix b, so b. So this means okay, we can let it 0. Well, this is always greater than 0. Oh, well, we know that, yeah. Let's see. Why is a non-decreasing function? Oh, by mean one is 0, right? So a equals 0, b equal to 1. So is it not by mean one 0? I don't know. So just let's say it's non-decreasing function for now. Okay, so forget it. So if it is a non-decreasing function, so we got our initial case. Let's do the inductive case. I forgot why, but and I can't think it right now. So in inductive case, fx is greater than equal to, we assume this is true. Assume this is true. And then we're gonna do so now we can let fx equal to g prime x. Then g prime x is less than equal to g k plus 1 k x k, right? And now we take the derivative on both sides. So this becomes gx is less than g k plus 1 and k factorial xk. But this is just xk plus 1 k plus 1. So gx is actually less than equal to this. So now that's proof that completes our second claim. Now let's let x equal to 1 in equation star. So f1 is less than fk1 k factorial for all k. But we know something about this, right? Limit k goes to infinity equal to 0 by claim 1. Okay, so that means f1 has to be less than equal to 0. But everything, but we know f1 equals 1 by assumption. So contradiction. And that's your proof. Now let's see why this is an increasing function. So let's look at this carefully now. Okay. So f has to be an increasing function y. So claims 3 is non-decreasing function. That's what I should say. Okay. So let's see. Mean volume zero. Again, this has to be mean volume zero. Did I not read the mean volume theorem correctly? It's mean volume theorem. Yes, it's mean volume. God damn it. Let A and B. Okay. Let A equal to 1. Let A equals to x, B equals to 0. Let's see what happens. So FB0 minus Fx equal to some C minus x. So Fx to negative x of C. Ah, okay. Okay, I see why. Okay, I see. Fx is greater or equal to 0. Okay, so the negative sign cancel. X is less than 0. Fc is assumed to be always greater or equal to 0. So here's a problem. This side is always positive. I mean, this side is always negative. This side is always positive. It's less than 0. So that means this whole thing has to be 0. So so we just proved, at least for, okay, so fx has to be 0 for x less than or equal to 0. Okay, so this is, so on this side is monotonely 0. Now let's see if we do this from the other way. So let's move it to this side. Once again, we choose b minus fa. Does it work? Oh, let's see what happens. So b, let's choose a equals 0. A equals 0. Then let's choose b to be 1. So this is 1. This is 1. So fc prime is equal to 1. Okay, so 0 to 1. This is a non-decreasing function. So okay. Wait. What am I doing something wrong here? Why is it not working? What am I trying to prove? I'm trying to prove it's non-decreasing. I'm trying to show. I'm trying to show this is non-negative. It's greater or equal to 0. Yeah, I just showed it. God damn, I don't know. What am I doing? Okay, this is always greater than 0. B minus a, this is always greater than, this is goddamn greater than 0. That's it. Alright, that was easy. That was, okay, that was too easy. Okay, so this is true. There is no proof. Okay, so that's it. That's how you solve this problem.